All right, I'm our last presenter tonight, so here soon. 5 minutes, actually. Okay, and I am just a PhD student here, and I wasn't nervous until I watched all of the other fabulous presentations. And now, well, I guess I'm standing on the shoulders of giants because I've been working with tangible landscape and grass since I got here a couple of years ago. And tangible landscape, if you're not familiar, is a tangible user interface for grass. And it was actually developed by Brendan and Anna back before my time here. And so there's Brendan in the photo. And basically, it's a system that I have one right here, so you don't even have to look at the TV. We've got a 3D model of a train on the table that we usually either CNC route or is made out of sand. Above it, there's a Connect scanner, like Xbox for Connect, if you remember. And that's scanning the train and passing the information to grass. And then you can run whatever grass workflow you want on it or Python workflow and then project the results back onto it. And so before my time, again, this was used for tons of applications, both in my lab group and around the world. And so here are just a couple of highlights been used for like coastal inundation. We have a pest and pathogen spread group here. And so here they are using it to forecast the spread of sudden oak death in Oregon. Brendan was part of a park planning exercise where it was like coupled with Blender, used to explore voxel data if you want, and teaching geography concepts to high schoolers. But when I got here, I was part of a project with Dr. Jay Levine back there, and we were looking at water quality in Eastern North Carolina. And Eastern North Carolina has, well, as you can see on the map, it's one of the top swine producing regions in the country. It also produces a lot of poultry and has a lot of cattle, and they also have degraded water. And so our question was, oh yes, and a piece of that is that a lot of the waste from these animals, they spread on the field as nutrients for the crops, which might seem like a perfect circle of the crops gets, or the fecal waste gets spread on the field. Uh, it fertilizes the crops, and then uh, those crops can feed the animals. But in reality, sometimes it runs off into the waterways. And so one of the questions that we've been thinking about is if there are different strategies we can implement at the small parcel level scale that will help kind of slow this waste from hitting the waterways during an intense rainstorm. And so that could be like implanting some vegetative buffers, maybe strip cropping or making some berms or changes to the topography. And us grass folk know that grass has a great overland flow model for that called SIMWE. And that was also developed by my advisor and her husband, Dr. Helena Matasheva, now like almost 2 decades ago. And so here's our little imaginary farm in Eastern North Carolina where they're spreading some sort of fertilizer on the field. And then we're running a 15-minute really heavy rainstorm and watching where the particles will go. And so we can inform how those particles move using land cover. And so we can use the land cover to set things like Manning's or the infiltration rate or the vegetation interception, and then feed those as inputs into SIMWE. And so here's my little code, since most people had at least one line of code. So this is like our SimWater, SimWe, and what's great is that grass or tangible landscape can modify all these inputs. We can change the elevation, we can change the rainfall excess and infiltration and Mannings by changing the land cover using like felt patches and things like that. So we can pretend to plant some vegetation on the terrain and then see how it would change the particle movement. And so I was lucky enough to implement this last year. And you can see in the video that's totally working. Yeah, that you can decide where you want to spray your fertilizer, and then you can run the particle flow in the like default land cover arrangement, and then you can add some berms or different elevation features there, maybe make some steps on the terrain, and then you can use the felt to plant riparian buffers or add rows of crops. And then you can run SimWe and it will give you a score that reflects what percentage of the particles did not end up in the waterways. And so I was lucky enough to present this work both with some folks who were in local government in Eastern North Carolina and as part of a study looking at how this system could help middle schoolers learn about agricultural runoff in Eastern North Carolina. And this was a big collaboration. I couldn't have done it without Jay Levine and my advisor, Helen Tasheva, Gail Jones at the College of Education, and I'm proud to be the dozenth presentation to recognize Anna for her contributions, and Emma and Amber. So thank you.